Okay, so the purpose of this video is to introduce the concept of block protection diagrams, how to draw them and what they're used for. So I'm going to start by drawing a very simple transformer feeder. There's the, let's say, 11 kV buzz bar with a circuit breaker that then feeds down a cable to a transformer. We'll also do a incoming circuit breaker, and then right at the top of the picture there is a DNO circuit breaker operated and controlled by the DNO. So let's put some protection on there now, and we'll start off by putting in a box for overcurrent and earth fault protection. So these will be either separate relays or a single relay. What we're also going to have is some differential protection. This isn't that common, but we're seeing more and more of it, especially on the larger sites. What I did forget to put in, of course, was the low voltage air circuit breaker. So the incoming circuit breaker will have another relay. Typically this could be a CPAM or a MICOM. I won't separate that out into the overcurrent and earth fault. In order for a circuit breaker to do something, it's got to have a means of operating. So these little rectangles are shunt trip coils. Now let's look at the transformer. The transformer's got quite a lot of protection, really. It's got oil level, it's got gassing, and it's going to have, even if not the other two, it's going to have a winding temperature. Now what I'm going to do is draw these as two separate boxes. Another one for oil level, or low oil, another one for gas, and then a final one for winding temperature. The low voltage ACB will also have a shunt trip coil built in with overcurrent, probably all as a single unit that manifests itself as something like a micrologic relay. Another typical item on site is a emergency push button. Now these little circles are meant to indicate the current transformers. So here I've got one on the main feeder, and that CT feeds into the overcurrent and earth fault. On the LV side of the transformer, we've got one that goes into the local micrologic. Again, you wouldn't normally see these separately, they're all in the same unit. And because we've got differential protection on here, we're going to have another set of CTs. Now, we don't know with differential protection what is the zone, but the block protection diagram will show the zone. So here I'm drawing another current transformer and connecting these two new current transformers to the differential protection, and that goes right down to the second CT. So now that we can see that any fault in that zone between the two will cause the differential protection to trip. I'll describe the issues with the differential protection, particularly for transformers, at another date. Now here we've got the output from the transformer feeding into the winding temperature, overload, low oil, and the gas. What I'm going to do is show that these three elements go into an alarm. So we want them to, before they get to critical proportions, we want them to hit an alarm. So we can see that the first stage actually operates an alarm. Now the winding temperature will only operate if the transformer gets hot, but the transformer will only get hot if there's an overload on it. So we could actually get it to just take the load off the transformer and then it would cool down. If there was a proper fault, then we would see loads of fault current. But in this particular case, we're going to, I've drawn it wrong here, but we'll take that to the winding temperature. So the winding temperature here only operates that low voltage ACB. It could very easily also operate the upstream. And what we sometimes find, and I haven't drawn it in here, so what I was indicating here is that the fact of the LVACB opening could also trip the circuit. So these lines are the wires from the current transformers into the protection relay. But then what is it that the relays actually do? So the shunt trip coil here will, if it gets a voltage, cause the circuit breaker to open. Now what I'm drawing here is something we don't often get. These are flag indicators. So this is quite helpful, so that if the overcurrent or the earth fault operates, they will actually flag. And if the whole site is off and the relay's dead, these could be mechanical operated relays that would flag. On the incoming circuit breaker, we've got exactly the same thing. We've got CTs, and that will operate the shunt trip coil. So what does the differential protection do? It hits the same trip coil, but I've drawn it separately just to try to make it clear. The whole purpose of these drawings is to make things clear. So now you can see that the differential protection hits the shunt trip coil on both circuit breakers. So any out of balance between the two sets of differential CTs will cause both circuit breakers to operate. Now what we typically want is an emergency push button to cut off all supplies to the unit. So here I've drawn it so that it operates the DNO circuit breaker. It might be that we have another EPO, because that distance could be quite big, and that EPO would operate again the DNO circuit breaker. But if this one was to only operate the upstream, then it would just hit the shunt trip coil on the main feeder. So what I'm trying to show here is that I've got an alarm, but I haven't got anything to trip. So now I'm drawing a not very neat line. If this was AutoCAD, you'd relay out everything, but it shows quite clearly that a low oil, not an overload, a low oil and a gas alarm would operate the shunt trip coil on the main circuit breaker. Now if this was restricted earth fault, we'd have 3 CTs on the windings and 1 on the neutral. Now what would you want the restricted earth fault to do? Well, it's restricted because it's between those 4 CTs. So that goes into the restricted earth fault. Now it's no good just tripping the LV side, because it's a fault on the transformer, and tripping the LV side wouldn't do anything. So what we would do is get the restricted earth fault to operate the shunt trip coil on this circuit breaker, and supposing you had an overcurrent or an earth fault or a differential or any other fault, you wouldn't know what would happen, what had happened. So we put the flags in like here, then we can actually see a mechanical device, and we have to reset that. And it's extremely helpful.